All right, hello everyone, Professor Dustin here, and this video is going to be about an introduction to Gauss's law. So Gauss's law is all about flux, which we have been studying in class. So let's just recall what flux actually is. So the flux, which is a property of the electric field, which are represented by my lines here. So the flux through any area, so the area, remember, doesn't have to be like a physical area, it can just be a region of space. So if we have like some circular area here, the flux is the amount of the electric field that goes through that area. Formally, that's the integral of the electric field dotted with the area, and the area being represented by a surface, which has an area, and a direction indicated by a normal vector. So we've been studying this. This is what flux is. Now, Gauss's law is an addition to this theory, which allows you to come up with how the electric field is actually created by studying how much flux goes through such an area. So the first thing to think about is not just some random area like this, but let's pick a specific kind of area, something called a closed area. So a closed area is very natural. It's instead of something that has a boundary like this, which like stops, a closed area is an area which completely encloses some region. So let me draw one of those. So that cube is an enclosed area because it completely encloses some region of three-dimensional space. This is not a closed area because it doesn't enclose a region of three-dimensional space. Inside this closed area, let's think about what the flux is. Okay, so we could be careful about this, and I think we probably should be careful about this, but at the moment, I'm just going to look at it and decide that it's pretty obvious that the flux through that area is 0. And basically, the reason it's 0 is because all the electric field that's entering the region is also leaving the region. Now, we'd have to be really careful to actually do that carefully to make sure that like the surfaces are perpendicular to the electric field. These surfaces are parallel to the electric field, so they don't contribute to the flux. We've talked about that kind of stuff. So we have to be careful, but I'm going to make the claim that the enclosed area, the flux is 0. So, okay, maybe that's just a special property of enclosed areas, but let me draw you another example where it seems pretty clear that enclosed area does not mean 0 total flux. So I'm going to do the same thing, but for a single point charge Q. So first, let's add the electric field. And now let's add the same enclosed area that I drew over here. So that's the cube, that's right there. But now it appears that the flux is not 0 through the area represented by the cube because all the arrows from the electric field are pointed outwards, right? Remember, this thing is the electric field. So the flux appears not to be 0 here. Just by the same argument that we had over here, all the electric field that goes in appears to go out. Here, no electric field is going in, it's all going out. So it appears that the flux definitely can't be 0 there. Okay, so that brings us to like, what is Gauss's law all about? Well, Gauss's law says there's a relationship between the flux and the amount of charge that's inside the region you pick. So that's the statement of Gauss's law. It only applies for closed surfaces. So I really should always, every time I write Gauss's law, I should always write for closed surfaces. But for a closed surface, if you calculate the flux using this, then whatever the flux is, it's going to be the total amount of charge enclosed by the surface divided by epsilon naught. So remember, epsilon naught is related to the Coulomb constant, where Ke is our normal Coulomb constant. This epsilon naught value is just another way of writing the constant. So you could actually replace this epsilon naught with 1 over 4 pi and the Coulomb constant if you want. It just is a little bit more conventional to write it this way, but they're totally the same. Okay, so this is kind of an insane thing, right? So the flux is this complicated thing where you have to like do all these integrals and make sure the directions match, make sure the shapes are right and all this stuff. But apparently, if you pick an enclosed surface, meaning not an open one, but just one that encloses some space, the answer to the flux is like, who cares about that? It's the total amount of charge enclosed divided by a constant. It like could not be easier. So let me just give you some examples about how like crazy simple this makes some problems. So I'm going to start with just writing a collection of charges. And I'm going to give them actual values, not just random Q's, but some actual, like, let's do nanocoulombs, but yeah. So there's just a bunch of random charges sitting out in space. If I was going to draw the electric field lines for these charges, it would be insane, right? I mean, okay, the electric field lines will go outwards here. Here they would go inwards, so these guys are somehow connected. There's another positive one here, so those guys are connected, but these guys are repelling each other. Like, it would be really hard to try to draw the electric field here. So if I'm going to say that, let me now try to ask what the flux is around some surfaces. So let's draw a couple of surfaces. So there are three surfaces. A1 is this guy, A2 is this guy, and A3 is this guy. I've totally done them randomly. I didn't put any thought into that. I just like draw. Okay. Now using Gauss's law, using this, it would be crazy to try to figure out what the flux is of the electric field through these surfaces. But using Gauss's law, it becomes just the easiest thing we can imagine. Whatever surface we're looking at, we just take the total charge enclosed and divide it by a constant. So like if I want to figure out what the flux is through A1, I add up the charge, 1 minus 10, divided by epsilon naught. Now I'm not being careful with the units. Yes, there are units for charge. It is definitely coulombs. The flux is going to come out, in Newton per coulomb meter squared if we're going to put the epsilon in. So not worrying about the units yet. That's the answer. So like instead of spending all day doing a bunch of calculus, I can just go bam, got it, right? Now obviously there are things about Gauss's law that we'll study that make it a little bit more complicated, but from the get-go, figuring out the flux through surfaces is could not be easier. So let me just do the other two. That's the flux through the area, the second surface, A2. It's got no enclosed charge. So in this case, all the electric field lines that go in also go out. So the flux is 0 through that surface. Cool. A3, the flux through A3, I just have to go 1 plus 3 minus 13. 4 minus 13 is what? Minus 9 again. Okay, well, I didn't mean to make them the exact same, but that's what happens when you just randomly make up some charges. Am I right? Okay, anyway, so those are my flux through those surfaces. Not doing this crazy thing, just doing Gauss's law. Now, obviously, there's more interesting things we can do with Gauss's law. That will be the second half of this video. But at first glance, this is what Gauss's law says. It just says that the amount of flux, the electric flux through a surface has only to do with the amount of charge that's enclosed within that surface. Even worse, these don't even have to be points. I could just I could have made a little bar. As long as it's got the same charge as that, it's got the same flux. So we haven't even talked about how to find the electric field from a bar like that. You have to do some calculus, right? But who cares? You don't have to if you just want to figure out the flux through a surface, it's bam. If I change the area of this surface, right? If I made it so that it was bigger, let's say instead of making it go like that, I was going to go make it bigger like that. How does that change the answer? Doesn't at all, because although I've made the area way bigger, my integral would just be, again, super hard. The fact that the area is bigger doesn't matter. The same amount of enclosed charge is there. Okay, so I'll stop at this. Go on to the second video to see really how this is more useful than this sort of a tricky way to calculate the flux through surfaces.